그냥 시작하도록 하겠습니다. Hello, my name is Baek Seong-Eun. I'm a master student at Armede. The paper I will be presenting today is GOLLuM, Gaussian Process Optimized LLMs, Reframing LLM Fine-Tuning through Bayesian Optimization. And it is introduced at the iCareer 2025 workshop. And the professor shared this paper, and as I studied, I think it would be a general purpose framework that would be used generally for various tasks. So I decided this paper. Before introduction, I'd like to point out that this paper specifically focused on chemical reactions, but I think this framework can be applied to various domains. Large language models have demonstrated remarkable capabilities in natural language understanding and generation. They can capture subtle data patterns, relationships, and the domain-specific knowledge. However, LLMs inherently face limitations in reliability due to issues like hallucination. This can be a critical problem in real-world domains, such as drug discovery and materials design. Therefore, uncertainty quantification becomes essential when applying LLMs to these fields. In this context, Bayesian optimization serves as a powerful framework. BO is particularly useful when optimizing functions that are expensive to evaluate. Recently, there has been growing interest in integrating LLMs into BO framework, especially by using LLMs as feature extractors for surrogate models. However, such approaches underutilize the LLM's adaptation capabilities. Moreover, they tend to decouple prediction performance from uncertainty estimation, which ultimately limits the effectiveness of optimization. To address these challenges, the authors propose a new framework called GOLLuM. This framework integrates LLMs into a Gaussian process architecture through deep kernel learning. Unlike previous approaches that use LLMs only as encoding tools through embedding, or treat them like lookup tables via prompting, GOLLuM enables a joint utilization of LLMs and the GPs within a unified model. A key feature of this method is the bidirectional feedback loop. First, the Gaussian process guides updates to the LLM's upgrades, encouraging it to produce more informative embeddings. In turn, these refined embeddings enhance the GP's probabilistic modeling capabilities. At the core of this feedback loop is the idea of redefining LLM fine-tuning as GP marginal likelihood optimization. This formulation encourages the learned embedding space to satisfy the principle that inputs with similar function values should lie close together in latent space. Without explicitly defining a contrastive loss, it naturally induces a contrastive learning effect. The result is a well-structured latent space that improves exploration during Bayesian optimization, while also maintaining well-calibrated uncertainty estimate. To summarize the contributions, the authors propose GOLLuM, the first framework for joint training of LLM and the deep kernel Gaussian process architecture. And through extensive experiments, they provide insights into the representation factors critical for successful Bayesian optimization. Finally, they demonstrate the strong generalization performance. Even when trained on a single data set, GOLLuM consistently performs well across various benchmarks. Then, what is Bayesian optimization? Bayesian optimization is a sample-efficient method for optimizing black box functions, potentially expensive to evaluate. Let me begin by explaining Bayesian optimization with a mathematical. And at its core, Bayesian optimization can be seen as the process of finding the optimal input, x star, that is the maximum value of an objective function from a set of possible inputs x. Let's look at a simple example. Suppose we have a pool of candidate inputs, x pool. This pool represents a limited set of experimental conditions for molecular structures. Each element in this pool encodes a different experimental condition, such as temperature, solvent, ligand. Let's say we vary temperature A from 0 to 10 in increments of 1. So total 11 values. And the solvent choose from 3 different solvents. And the ligand have 5 different types. That gives us total of 11 times 3 times 5 equal 165 possible combinations. So in this case, M equal 165. However, testing all of these combinations through actual chemical experiments would be extremely costly and time-consuming. That's why Bayesian optimization becomes powerful strategy. BO helps us identify the experimental condition most likely to yield the best outcome without having to test every single possible input. Bayesian optimization typically uses a surrogate model, and the most commonly used one is the Gaussian process. So in this equation, fx follows a Gaussian process with a mean c and the covariance as a corner function. The Gaussian process models the unknown function using a corner function. Simply, a corner function measures how similar two input points are. There are many types of corner functions. In the case of GOLLuM, it uses the bottom 5 halves corner, because it is broadly applicable to continuous Euclidean representations. The bottom corner includes a train of hyperparameters, collectively called theta. These include the length scale, variance, and constant mean of the function. Length scale is a criterion for how far we can judge similarity. And the signal variance is a measure of how sensitively we will react to data values. And the observation noise variance is a measure of how much noise we can expect to be added to the data. And the constant mean determines the baseline of set of the data. These hyperparameters are updated dynamically as new data becomes available, allowing the model to better adapt and refine its prediction over time. And the Gaussian process uses a bottom corner, and it requires a continuous input. This is because for discrete inputs, it's not possible to meaningfully compute Euclidean distances between points. However, in our case, we are dealing with heterogeneous data types, including categorical data, numerical features, and the molecular structures. Therefore, we need to convert these inputs into unified continuous embedding. To do this, we first define standardized templates T. Each template is a structured representation that includes the parameter name and their corresponding values for a given experimental setup. Once we have this structured template, we use LLM to convert it into a fixed dimensional continuous embedding. These embeddings act as a unified representation of different parameter types, allowing us to feed them directly into the Gaussian process tunnel. Since the LLM embeddings are used directly as inputs to the Gaussian process without any additional processing, we become fully dependent on the pre-trained LLM's embedding space. However, general purpose pre-trained LLMs typically do not contain sufficient knowledge of chemical similarity. As a result, these LLM embeddings often fail to encode an inductive bias that is appropriate for use with a Gaussian process. This issue is further supported by experimental results. We observe significant performance differences in Bayesian optimization, depending on which LLM is used for embedding. In this figure, domain specialized models like DRFP or T5-CAM consistently show superior performance than other general purpose models. In conclusion, a better representation helps the PO to be applied more effectively. This highlights the need for fine-tuning the LLM embeddings to make them more suitable for use in Bayesian optimization. So to address this, we introduce a feature transformation function, G5. This transformation function maps the original LLM embeddings into a task-specific representation space. These transformed embeddings are then used as input the corner function, which is why we call the resulting model LLM-based deep corner. There are three main strategies for designing the transformation function. First, using a projection layer on top of the LLM embeddings. Second, fine-tuning the LLM itself using LoRa without adding view layers. Last, a hybrid approach, which combines both the projection layer and LoRa fine-tuning. As a result, our framework involves optimizing two sets of parameters, theta and phi. Theta is the hyperparameters of the Gaussian process corner, and phi is the parameters of the transformation function. We perform joint training by maximizing the marginal likelihood of the Gaussian process. This allows both theta and phi to be jointly trained in a way that aligns the inductive biases of the GP with the learned LLM embeddings. And we compute the gradients of the marginal likelihood with respect to the parameters via standard backpropagation. This joint training process ensures that the embeddings produced by the LLM are well aligned with the behavior expected by the Gaussian process model. It leads to a more effective and domain-aware application of Bayesian optimization. So, Bayesian optimization using an LLM-based deep corner Gaussian process can be summarized with the following pseudocode. First, the input data is passed through the LLM, and using these embeddings, we compute the Gaussian process marginal likelihood, and then update both sets of parameters, theta and phi. This process is repeated iteratively until convergence. So that is until we find a suitable set of theta and phi that best explain the data. Once training is complete, these parameters are used for finding best input during test time. In the test, when we are given a set of candidate inputs, we first convert them into embeddings using the LLM. Then compute the acquisition values for these points based on the current GP posterior, and the BO suggests the next input to evaluate by selecting the ones with the highest acquisition values. This is how the full BO loop operates in the GOLLuM framework. In a Gaussian process, the corner function produces similarity scores based on the distance between inputs. As a result, during marginal likelihood optimization, the embedding space is fine-tuned so that similar inputs are placed closer together, while these similar inputs are pushed further. This naturally leads to an effect similar to contrastive learning, even though we never explicitly define a contrastive loss. This effect arises direct from the GP's marginal likelihood objective because of the nature of the distance-based corner. In particularly, the term y transpose k inverse y term can be rewritten as a weighted sum of pairwise interactions between the data points. Therefore, even without defining an explicit contrastive loss function, we still benefit from an explicit contrastive effect, which helps align the learned feature space more meaningfully with the task. And introduce experimental results and analysis of the GOLLuM framework. We begin by exploring the relationship between Bayesian optimization performance and the trainable parameters within the Gaussian process corner function. In particular, we observe a strong correlation between the length scale parameter and the BO performance. This result suggests that when the representation space is well aligned with the inductive bias of the GP, we are more likely to achieve effective optimization performance. Next, we evaluate which type of LLM-based deep corners performs best within the GOLLuM framework. Across the board, all three approaches to implementing the transformation function G5 consistently outperform the traditional baselines in Bayesian optimization. This improvement holds regardless of the LLM architecture, whether it's encoder-based or decoder-based or encoder-decoder. This indicates that the performance gains are robust to architectural choices and not limited to a specific model type. And also, among these three methods, the combined approach, which uses both projection layer and the LoRa fine-tuning, consistently showed the best performance across all LLM architectures. This result suggested that the combined approach successfully leverages the strengths of both techniques. In doing so, it effectively captures the benefits of both representation adaptation and the structural flexibility. And in some cases, a general purpose LLM like T5 or QM model series actually outperforms domain specialized models. This suggests that high BO performance can be achieved even without a domain-specific model or a domain-specific input format. This result reinforces the importance of aligning the GP's inductive bias with the embedding space. And let's take a closer look at how the embedding space evolves during fine-tuning. I will refer to high-performing points as high and low-performing points as low. Since points in the high group share similar strong performance, they should ideally be embedded close to each other. Likewise, low points should also cluster together. In contrast, high and low points represent very different function values, so they should be embedded far apart. Initially, we observed that high and low points are mixed together in the embedding space. This suggests that the representation is unstructured and does not yet reflect task-relevant information. However, as Bayesian optimization progresses and the model continues to update, we can observe a clear separation in distance between the points. High to high and low to low L2 distance are more similar than high to low L2 distance. This structure evolution becomes even more evident when we visualize the distribution of LLM representation in the latent space. At the beginning, the embeddings are scattered without any clear pattern. It indicates a lack of semantic organization. But over time, we see that low value points begin clustering with other low value points, and the high value points cluster with the other high value points. We can also observe suggested points increasingly shift toward the regions associated with the higher objective values. For last, most suggested points are concentrated around the high-performing region, demonstrating that the model has developed a structured and meaningful embedding space. This clear separation in latent space offers interpretability. It shows that the model is not just memorizing data, but actually learning meaningful relationships in the task domain. Finally, GOLLuM demonstrates their effectiveness across a range of chemical benchmarks, showing that the framework not only works in controlled experimental settings, but also performs strongly in practical applications. So to summarize, this paper reframed LLM fine-tuning as a Bayesian optimization problem and proposed GOLLuM, a framework that enables joint training between Gaussian process and LLMs. GOLLuM directly addresses two fundamental challenges in BO. The first challenge, designing a meaningful representation, is addressed by using adaptive LLM embeddings that can capture task-relevant structure in the input space. The second challenge, selecting appropriate kernel, is handled through deep kernel learning, which enables the representation space and the kernel parameters to be jointly adapted to the task at hand. As a result, GOLLuM outperforms baseline method across multiple benchmarks, and its flexibility suggests that it can be extended beyond chemistry to a wide range of applications. And while reading the paper, I have some opinions. I believe that this LLM-based optimization framework could be effectively applied to vision language tasks as well. Just as we've seen the extension from LLM to Baek to VLM to Baek. There is great potential in combining multimodal representation with optimization. However, compared to methods that use LLM-based embeddings for optimization, I think that research on connecting multimodal embeddings, such as images or videos, to optimization tasks remains underexplored. One possible reason is the challenge of effectively encoding visual information into embeddings that are suitable for optimization. And additionally, it's still unclear how to formulate optimization problems in a way that meaningfully leverages such multimodal inputs. That said, if we can develop methods that both embed multimodal information effectively, and the reframe tests involving those inputs at the optimization problems, I believe it could lead to exciting and impactful new research topics. Oh, this is Thank you for listening.